I want to bring your attention to the source of this material, the Analytical Chemistry textbook written by David Harvey. It's open source. This material is contained in Chapter 4. When we consider measures of spread, the range is the simplest. It's the difference between the dataset's largest and smallest values. It's often noted, however, it's not typically used in a rigorous analysis. Random errors follow a Gaussian or a normal distribution. And if the errors are truly random, meaning there's no systematic error, overall results will follow this curve. What we have on the y-axis is the number of measurements of a given value. What this indicates is that most of the values are very close to the mean. And in fact, 68% of the values fall between the mean minus 1 standard deviation and plus 1 standard deviation. If we look 2 standard deviations out, that contains 95% of the measurements. 3 standard deviations is 99.7. This curve, this distribution, follows population statistics. We have more than 20 replicate measurements. We're going to see that there's 2 different versions of standard deviation, whether or not they're population standard deviation or sample standard deviation. The standard deviation for finite data sets is given the symbol S. We calculate S by taking each deviation, the measured value minus the mean, squaring it, and adding up all of those squared deviations. We divide by n minus 1 and take the whole square root of the whole mess. As we will see, we can also calculate standard deviation very quickly using Excel. In Excel, we use sdev.s. S tells Excel that this is a sample standard deviation and applies this formula. And that's followed by the cell range. We're going to frequently report the relative standard deviation, which is our standard deviation divided by our mean. It's a comparative value, as is the percent relative standard deviation. We can calculate the standard deviation, relative standard deviation, and percent relative standard deviation of the same sample of pennies with their masses. We've previously calculated the data set mean as 3.117 grams. Next, we can calculate the quantity of xi minus x bar squared for each of these values. Okay, we see the details of this first calculation. Xi minus x bar quantity squared is going to give us this value, and I'll do that for the rest of the 7 values. All right, so we have all 7 of these values. Okay, we can add them together to get our sum, and that's going to be our value here in the numerator, and we can go ahead and calculate our sample standard deviation. And we have our value for our sample deviation. Our relative standard deviation is going to be our standard deviation divided by x bar. And our percent relative standard deviation is our standard deviation times 100%, which is 1.6%. All right, we're also asked to calculate the variance of the example. Variance is equal to the square of the standard deviation. and here is equal to 0.0026. As we mentioned before, there's differences between population statistics and sample statistics. You see that there's significant similarity. However, the sample standard deviation is replaced with the standard deviation sigma, and the mean is replaced with the true value. In general, as n goes to infinity, as you have more samples, more replicate measurements, x bar goes to mu and s goes to sigma.